Okay, so when we finish this, you should be able to tell me what theoretical yield is, what percent yield is. You should be able to calculate them. You should be able to take that whole conversion from like maybe where you're given a percent or grams of one thing and get all the way to what you want to know. The other thing we're going to cover is the chemical formula of a hydrate, which we've used a lot of hydrates already. The lab that we just did where you used the sodium bicarbonate and the HCl and you drove the water off to find the anhydrous form of sodium chloride. You used a hydrated chemical. So you have to be able to figure out how much water was there. So let's start with theoretical versus actual yield, which should kind of make sense. When I say theoretical yield, theoretical is really the quantity of a product calculated. To form when, I'm going to say when all the limiting reactant is consumed. So we know how to figure out the limiting reactant. When it's all used up, I can use those numbers and I can calculate my theoretical yield. That's like in a perfect world. Then I have my actual yield, which obviously equal to what's actually produced, what you get. As a result of the reaction. So that's what you get as a result of the reaction. Now, in that lab that we did with the evaporation or the driving off of the water, think about that for a minute. How close was in that particular lab, your actual yield to your theoretical yield? Do you remember what the theoretical mole ratio was?
1 to 1.
1 to 1, good. And most of you, if I recall correctly, were pretty darn close to that, yes? I mean, I had a lot of like, I don't know, 1.015s, 1.021s. A lot of you were very close. I think only in 1 or 2 instances did we have some that were off, and that was by way of things like we had the wrong watch glass mass, or we never did figure the one out, did we, Avery? Avery and Rachel, where that came from, I think that was just a balance error, probably. But your second trial was spot on. So, and that was the same way, Max and Laura, that was the same way for you guys too, wasn't it? When we like figured out that we had switched the watch glass, it was all very good. But it doesn't always turn out that way. We know that. So we need to talk about some things that might be the reason for the difference. And the first one is pretty straightforward and pretty simple. Some of the reactants don't react. Perhaps the reaction doesn't go to completion. We could also say that some of the reactants may react in a way different than what's expected. And then we also just need to be aware It's not always possible. To recover all of the product. From any reaction. Now, I want you to think back to that same lab I've been talking about, where we drove off the water. When you added the two reactants together at the very beginning, what happened to many of you? Do you remember? Like if you looked in the area around that evaporating dish? What, Rachel? What? Yeah, some of the solutions sort of bubbled out or popped over and you had like a white residue ring around your evaporating dish. So that might be a case, you know, where something unexpected happened, or a case where you may have lost just a little tiny bit of what you were trying to recover in the end. So you have to look for things like that. All right. So if we look, percent yield is a way to look at our outcomes from lab and kind of look at how well we did with what we were working with. So when I say percent yield, I am talking about a way to, we'll say it relates actual yield to theoretical yield. So I can say that percent yield is equal to actual yield divided by theoretical yield times 100. Actual yield divided by theoretical yield times 100. AY TY times 100. That's a little hard to read. Now, let's look at, let's just start with example problem number 1. Take a minute and read that. And I was nice, I gave you a formula. In this one, you don't have to write out the formula.
Jaden, keep him out. Jaden, keep him out.
All right. Check out your reaction. What you're starting with, what you're ending with. And it says, assume that you carry out the reaction with 25 grams of cyclohexane, C6H12, and that cyclohexane is the limiting reactant. So there, you didn't have to figure out the limiting reactant. It's spelled right out for you. What is the theoretical yield? It's asking you for that. And then it asks you to find, in letter B, it's asking you to find the percent yield. So first we have to see, this is what we got. What should we have gotten? So we have to start with what we're given, which is our 25 grams C6H12. That's our given. And we're also told that this is the limiting. So we know that's what's going to stop the reaction. So I'm going to start this by going from grams to moles of C6H12, just like we've been doing. So I've got 25 grams of C6H12, and I want to get it to moles. So if you don't have your calculator out, pull it out. What's the molar mass? Anybody got it yet? What? 84, thank you. So I have 84 grams of cyclohexane and 1 mole of cyclohexane. Now, tell me how many moles that is.
Not easy. 2 million.
Now make sure you agree with that. Yes? So I have 1 yes, I have 2 yeses now.
Well, that's
Good?
Fairly likely.
Alright, so now I have moles of cyclohexane. I want to know about adipic acid. So I have to use my mole ratio. So I'm going to go moles So let's use our mole ratio. You've got the equation on your paper. I didn't write it above. So I have 0.298 mole C6H12. And I'm using my stoichiometric equivalencies for every 2. I have 2 adipic acid.
Were we supposed to do like 2 C6H12 originally? Or you disregard the 2? Or disregard it?
You mean up here?
Yeah.
No, you just use what you want to know about 1 mole of it.
Okay.
So really, these guys cancel each other out.
Yeah, the 2. So we can
7.2.
divide multiple.
All right. Everybody follow that? Questions? I've got a 2 over a 2, so that's just like a 1-to-1 ratio, so I know I have the same moles of both. Now I'm at moles of adipic acid, and I want to go from moles. Yeah.
How do you just know to start this part of like that? Like from the problem, how can you just tell what to do after?
Because you always have to start to work with what you're given. And I know that in these problems, I'm going to have to use a mole ratio. So when I'm given grams, I should know I want to get that to moles right away, because then that lets me use my stoichiometric equivalency from the reaction that I'm given, or the reaction that I've written. So that's pretty much always what you're going to do. If it were a really easy problem, they would have given you like, or I would give you one of the percents to begin with, or one of the numbers. Like maybe I would give you the theoretical yield and you would have to find the actual yield. We'll do a bunch of different kinds. All right, so let's take moles, H2C6, to grams. So do that. Josh, what'd you get for your molar mass?
Oh, I worked all day. Let's see here. For which one are we
Your
finding?
molar mass. What'd you get for your molar mass?
The 43.5.
No. What'd you get for your molar mass of your compound? You're a step ahead.
Oh, goodness.
Oh, goodness.
146.
There you go.
There we go.
146 grams
That's what I was looking
per mole. And what was your answer, Josh?
for. 43.508.
43.508. grams. Now, that tells me what I should have gotten. Is that what I got?
No.
No. Where do I find what I actually got as my yield?
B.
From the problem, right? In letter B, it tells you. So now we're going to use our percent yield is equal to actual yield over theoretical yield times 100. So within the problem, I told you that you obtained 33.5 grams. So that would be your actual yield. And we calculated and found that we should obtain, I forget, 43.5. Now we multiply that by 100. I'll let you do that.
Would you always give us the theoretical yield?
Yeah, one or the other usually. Yeah, there are really long problems where you could solve for both, but normally you'll have one or the other. And you might have the percent yield and the theoretical yield and have to find the actual yield. You might have to manipulate the equation, but yeah. So how did we do? What's our percent yield, Annika?
I got 77.
She got 77.
35.
Let's see,
I got
33, is it 33.5, 43.5?
Oh, that's why. I did 44.5.
Yeah,
That's
77%. Okay. What's next? So here's the next lab we're gonna do. We're gonna talk about hydrates, which we've been using all along.
Yeah, Carter.
So this is, when you hear the word hydrate, and it has to do with the chemicals we're using, this is actually a chemical compound with some parts water. So sometimes you'll see it written as like CaCl2, and you see a little dot, and it might say NH2O if it doesn't want to tell you how much water, how many moles of water. You might see something like CaCl2XH2O. You'll see it both ways. Remember that N can stand for numbers of moles. Or if you're actually given that, it would say CaCl2 with, that dot means with, 4 H2O. When I say this, I would say calcium chloride with 4 parts water. Okay, so let's look at this problem. 15.67 gram sample of hydrate of magnesium carbonate was heated. So let's talk about that formula first. Hydrate of magnesium carbonate. In your notes, write the formula for magnesium carbonate. You should be able to do that. What's my charge on Mg, Kinley? 2 plus. Carter, can you tell me the formula for carbonate? CO3 2 minus. Colin, what's my chemical formula? Mg, that's nice. They just cancel each other out. Mg, CO3, and then it says hydrate. So then I would put, doesn't tell me how many parts, then I would put some parts water. So I'm going to heat it, it decomposes, drives off the water, the mass was reduced. Okay, and then it says what's the formula of the hydrate. So if I'm heating it and the mass is reduced, what am I driving off?
Water.
Water. So that's a good place to start. I started with a sample mass of 15.67 grams, and I ended with, this is my start, this is my end, 7.58 grams. So if I use that and do the math, that tells me how much water was driven off. So do that. Stuart, what'd you get? 8.09 grams of water. And I know by what I was left with, right, that that's my magnesium carbonate. So I have my grams of both. So now I'm going to take my grams of both and go to moles of both. So you're going to work with your H2O and your MgCO3. And I'm going to let you work through it. Then we'll talk about it. Everybody have their molar mass of magnesium carbonate calculated? Avery, what'd you get for that? Molar mass of magnesium carbonate. Did you do that yet? No. Addie, do you have it yet? 84.3? Okay. I just wanted to put that up so we had a check with each other. So find your moles and then stop. Bless you. Raise your hand if you're still calculating. Okay. Cooper, what'd you get for moles of water? 0.44. Okay. Everybody agree with that? All right. Who else have? Oh, Caleb, what'd you get for magnesium carbonate? 0.0891. Thank you. Kind of all said that in unison. Okay, so now what do you think I'm going to do? Mole ratio. Calculate your mole ratio, people. I have 1 mole of magnesium carbonate to max. How many moles of water? 5. Good. So now the last step, all I have to do is write my chemical formula. So I would write it, I'm going to replace my X. MgCO3 with 5 parts water.
Is that like a little dot you make in the middle?
Yeah, means with.
Gotcha.
Looks like a multiplication sign, but it's not. We're not multiplying.
I can't see, Josh.
Wear your glasses.
All right, flip the page. We'll do a longer one.
Oh, yay!
Yes.
For us?
That's all I've always wanted.
Just for you.
Christmas came early.
I'm gonna cry.
All right, let's read this one. This one's kind of a long one, but I wanted to show you one of each type. Okay, when you react 3.9267 grams of sodium carbonate with unknown parts water, oh, this should look familiar, with excess HCl, 0.6039 grams of gas is given off. What's the number of water molecules bonded to? So basically, we're asking, this is a hydrated formula. Okay, so let's write down what we know. 3.9267 grams Na2CO3. Now, that is all you're given. The next thing you're going to have to do, and this is exactly the equation that we did in lab. It's exactly the same thing. So when you get something like this, the first thing you're going to have to do is write the equation. You have to think about the 2 things you used, which are stated in here. You have to think about the gas that was given off. We had it in lab. The water that we drove off, and what residue was left in your evaporating dish. What were those 3 things? So I know I'm starting with Na2CO3, and what else am I starting with? Some HCl, because you're given that in the problem. Now, what was the residue that was left in the evaporating dish, Annika, from that lab? Do you remember? It was NaCl, good. And what were we driving off? Why were we heating? What were we getting rid of? Water. And what was the gas that was given off from this CO3? CO2. All right, now, this was a solid, this was aqueous, this was solid, liquid, gas. Well, now, I guess in the end, this is a gas. Balance that equation. Take a minute and balance it. So step 2 would be to balance. And I want you to write your stoichiometric equivalencies. Yes, ma'am. Because we talked about earlier, well, you were given the 2, you were given the reactants. And we talked about earlier about how when this CO3 is present, that it usually breaks down in one of the O's, hooks with your cation over here, and you always end up with CO2 gas. At this point, that's all the farther we've gone with that. And we're going to most likely be given, either given the equation or not given much past a double replacement at this point, because we haven't done a whole lot of this. That's why I used the one from lab. Lauren, am I correctly balanced? Yeah? Okay. So I'm balanced. Now I can write my stoichiometric equivalency. Any trouble with that? All right, so we are given also some information about the gas that was given off, so we have to use that. We have 0.6039 grams, it says, of gas that was given off, so we would call that the CO2. So we're going to have to use that. That's really the only other thing we're given, other than how much we had up here. So let's take our CO2 and we're going to take, let's find our moles of CO2. So we just kind of have to work from what we're given in the problem.
How do you gonna start with CO2?
Because it talks about the gas in the second part of the problem, so we know we're going to have to use that to work our way down to find water in the end. Because we've got, that's one of the products. So we've got to find our products, because we know our products are going to equal, ideally, our reactants. So as we work through, I think it'll become a little more clear. So let's find moles of CO2 from grams of CO2. Okay, do we have a number? What'd you come up with? How many moles of sodium carbon, or how many moles of carbon dioxide do I have? Addie, what'd you get? 0.0137? Okay. Anybody get anything different than that? All right, so we'll use that. All right, so now I have my moles of CO2, and I can look up to my stoichiometric equivalency, and now I'm going to compare CO2 and sodium carbonate. And their mole ratio is 1 to 1, correct?
Why are you comparing?
Yeah.
Because I have the information about this, and that's my main reactant that I have information about. So I can say that that's a 1-to-1 ratio. Does that make sense to everybody? So if I have 0.0137 moles of carbon dioxide, I would have 0.0137 mole of sodium carbonate. So I now know my grams of CO2, I know my moles of Na2CO3, let's go from moles, and we'll do another one of these tomorrow to work our way through. Let's go from moles Na2CO3 to grams. And remember that master given in the beginning, that 3.9 or 3.8, 3.9, that has water in it. So we can't just flat out use that because we don't know what part is the water. What's my molar mass of sodium carbonate? Who have I not? Lauren, what's my molar mass of sodium carbonate? okay? So I come up with 1.45 grams of sodium carbonate. So now I know my grams of sodium carbonate, right? Does that make sense? And I also know my mass of what I started with, which had water in it, right? So now I can find, because I have grams of sodium carbonate. So in my problem, with the water in it, I was given 3.9267 grams of the compound with water in it, and I know the sodium carbonate part of the compound is 1.45 grams. So I can do that, and I can find my grams of H2O. So I just have to do that subtraction. So 3.9267 minus 1.45, 2.477 grams H2O. Everybody agree with that? All right, now what do you think I'm going to do with my grams of H2O? Make it moles, because in the end, I'm going to have to use a mole ratio again. So I'm going to go from grams of H2O to mole H2O. 2.47. You have a question, Josh, or you got an answer?
I have a question.
Yes.
So it says with excess HCl, so would that also be factored into?
We don't have to worry about that because it's a leftover. And because the question is asking us for the formula of the hydrated compound, we don't have to focus on the HCl. Now, if we were specifically asked a question about the HCl, we'd have to work this differently.
Okay.
How many moles is that?
0.13.
Point what?
138.
138? You guys agree with them? Okay. All right. Now, I know my moles of H2O. Do I know my moles of sodium carbonate? We found it somewhere. So my H2O is 0.13, is that right? 0.138 moles. H2O, and my water was, or I'm sorry, my, my water was what? 0.138. My sodium carbonate was 0.0138. Is that right? Check.
I think it's
137. Okay. Is that right? I have to go back here and flip back. Yeah. Yep. Okay, so this is a 7. All right, so now I can do my mole ratio. Hey, that's a pretty nice 10, isn't it? Clark, what's the final chemical formula? There's your final formula. Annika, did you get your question answered? Okay. That is about as long and drawn out as a problem can be with these particular ones. Let's take a little break. Get up, move around a little bit. If you need to use the restroom now, use the restroom, and then we'll come back, and we've only got, I think, one example left to do.